This is the review of the entire book, Math 2101. So no, it doesn't go into great detail with a lot of examples. I'll just use a few examples while we go over all of the key concepts from this book. And we're thinking about how the student needs to put these concepts together to be able to handle the situations they'll deal with in a final exam. A student who's strong enough, understands the details of the course well enough to be able to do well in the exam. The first thing that I'll mention, which comes from way back in chapter 1, but I'm not trying to stick with the chapters in order perfectly as I do this. It's about the concepts. The first thing I'll mention is translating English to math. So we have 4 examples here. Simple little examples where we're given the information in English, but in order to score points in a math question about each situation, we have to be able to translate the English language into math language, creating equations, defining variables, that sort of thing. So I'll quickly do that. I'm going to use these examples as many times each as I need to as I go across the different concepts of the course. So a boat taxi costs $10 to get in plus $3 per kilometer. That is a y equals ax plus b linear situation. And x is going to be equal to the number of kilometers. I'm defining a variable. Y is going to be equal to the total cost. And then I'm able to make an equation y equals 10x, y equals 3x plus 10. The b, the y-intercept, is the $10. That's the amount you have to pay. Even if you get in the taxi and decide not to go anywhere, you still are supposed to pay that $10. That's a constant term. So all these terminologies and concepts from the book keep on popping up as we do this. The 3 is the slope. It is not a constant term because it has to be multiplied by the number of kilometers. It's the cost per kilometer, so you would multiply that by the number of kilometers in order to figure out the total cost for that many kilometers. This creates 3x, which is a term that has both a variable and a numerical coefficient, and 3x and 10 are not similar terms. The constant term and the term with the variable x cannot be directly combined. We can't say 3x plus 10 equals 13 or 13x. So this is defining of variables, translating English to math, creating an equation y equals ax plus b, and then of course I can answer a question. So if we go 4 kilometers, y therefore is equal to $3 per kilometer times 4 kilometers plus 10, which is 12 plus 10, which is $22. That's how much it costs for that taxi ride. So we've translated from English to math, defining variables, making an equation, and then we're plugging values into the equation to answer questions from that situation. That's enough for this taxi example for now. The next thing on my list is about isolating a variable. I'd rather use a direct proportion situation, like for instance, each student uses up 7 pencils per year. To illustrate the isolating of a variable, well, if each student, that's one student, uses up 7 pencils, then how about 9 students? How many pencils will they use up? I took that information, I translated from English into math, and I created a proportion. The left side has to be equal to the right side, and I solved this with cross multiplication. 1x is equal to 7 times 9, which is 63. 1x means the same as x, and 7 times 9 is 63 pencils would be my unit of measure. Now here's an issue that I want to talk about. When students do the final exam task questions for this course, these are big questions, a big situation with a lot of detail, and you're expected to not just figure out answers, but to use the math that was taught in the book to find the answers. A lot of students don't seem comfortable with the idea of making an algebraic model. I am defining x as number of pencils, and I've created an equation. This is an algebraic model. But it's not the only way of making an algebraic model from this situation. I can say I'll still make x equal to the number of pencils. No. I'm going to make y equal to the number of pencils and x equal to the number of students. When I do it this way, 7 is my proportionality constant. I am making an equation in y equals kx form, which is y equals 7x. Now I can plug in the number of students I want and figure out how many pencils they use. So with my example from before, what about 9 students? It would look like this, y equals 7 times 9. Therefore, y equals 63 pencils. Same answer. And it's really the same math, because the idea of making a proportion is really the same thing as what I did here. I'm making an algebraic model in this y equals kx form, which is a proportionality model. K is the proportionality constant. So notice how I was able to make 2 different looking equations to solve the same problem from this same little bit of English. And I was doing all the same skills as usual. How about a lab situation where each pair of students, because the students do their labs in pairs, are allowed five Petri dishes. Okay, let's translate this into math. I'm going to do a proportion. 2 students use 5 Petri dishes. Therefore, we can ask a question. What about a class of 30 students? How many Petri dishes will they use? Okay, we have a proportion. We solve this with cross multiplication. Top times bottom equals bottom times top. Extremes, product of extremes equals product of means. We have 2x equals 5 times 30, but then what I'll do is I'll divide both sides by 2 before I'll simplify 5 times 30. So I still show 5 times 30 divided by 2. These cancel. I have x equals 5 times 30 divided by 2. I'm doing this to illustrate the idea of isolating the variable. I'm avoiding simplifying all these numbers because my goal is to get my variable by itself, which I did. X is alone on the left side. Now I can simplify. And I can do it in stages, I can do it in different ways. I can say therefore x is equal to 150 over 2, which is 75 Petri dishes. I've solved my problem, but to illustrate that, we can move things around in the equation until our variable is isolated on one side. I put this little problem here because these equations we're making are kind of easy. They're kind of too easy. The algebra happens so fast you don't necessarily notice it, but there was a lot of emphasis on all the basic algebra skills in the early chapters of this book. So how do we solve something like this? We have 3 constant terms, -3, -5, +2. We have a variable x. We have yet another number here which is being multiplied by the bracket. Multiplying across the bracket is a thing that happens in math. Students are expected to be able to do all of these little things. First thing I'm going to do is multiply across the bracket. I get 2x minus 6. 2 times x is 2x. 2 times -3 is -6. Now I'm going to combine these 2 terms. 2x minus 6 minus 5 is 2x minus 11. I'm able to do that because they're similar. They're both constant terms. Now I want all the x's on one side and all the numbers on the other side. So 2x minus 3x equals 2 plus 11. I've moved the 3x from the right side to the left side. I'm using the shortcut. I move the 3x to the left side, it becomes negative. I move the minus 11 to the right side, it becomes positive. I have negative x equals 13, and then I divide both sides by -1 because my variable is not isolated yet. Negative x, I don't want to know what negative x is, I want to know what x is. So I divide both sides by -1, and x is therefore equal to -13. I have my answer. Let's verify it. 2 times -13 minus 3 minus 5 has to be equal to 3 times negative 13 plus 2. If I did this right, I'll do the bracket first. Negative 13 minus 3 is negative 16. 3 times negative 13 is negative 39. Negative 39 plus 2 is negative 37. I'm finished on the right side. 2 times negative 16 is negative 32 minus 5. Yes, negative 32 minus 5 is negative 37. I have negative 37 equals negative 37. My verification shows that I did this correctly. These are the basic algebra skills that the early chapters make sure you know how to do, because you need to do them when you do algebraic modeling. You don't necessarily have to do all of this stuff with these small algebraic models that we're dealing with in this course. But these small algebraic models are introductory models to get the student used to doing this type of math. And it's just the beginning, because as you move up levels, you're going to deal with more algebraic models, more types of equations, bigger equations, and you're going to encounter more and more situations like this where you have to be able to do all the algebra skills in a multiple step problem, and they're not always so simple and small. We've talked about terms, coefficients, constants. Gas consumption. Here we go, gas for boat. The boat uses 20 liters for 100 kilometers, and the gas cost is $1.15 per liter. So 20 liters per 100 kilometers is the gas consumption. I have to know the cost of the gas, which I'm going to multiply, but I also have to know the distance of the trip. So what if I'm going somewhere that's 40 kilometers from here? Well, I'm going to multiply by 80 if I'm doing a round trip. If it's a one-way trip, sure, I would just multiply by 40. Students often seem to think this is intimidating, but it's a situation that really always works the same way. Now all I have to do is simplify this. 20 divided by 100, I can do that first. I can do a division. 20 divided by 100 is 0.2. And I can multiply that by 115 and then by 80. So I'll do it in stages. 0.2 times 115, 0.23. 0.23 times 80 is 18.4. I'll put a 0 there because this is money. So it will cost me $18.40 to do that 80-kilometer round trip, if this is the cost of gas and if this is the gas consumption of my vehicle. This is not a very difficult calculation to make. And it's a model. I can call this an algebraic model if I want. I can say, okay, let me do that down here. I'm going to erase a bit. This is one of the concepts, a key concept I think that's important for this course. When you're asked to use an algebraic model, because that's what the course is about, that's what the book is about, you can turn almost anything into an algebraic model. If you're doing any math, if you're doing any calculations, well, call it a model. So, especially multiplication. Multiplication happens a lot in this book, and the difficulty is it's too simple. The students get so used to doing these quick multiplications when they need them that they don't stop and think, hey, I can express this as an algebraic model if I want. And if I say, okay, now show me the algebraic model, they're going, what? What algebraic model? No, this is what the book is about. We can say A is equal to the gas consumption. B is equal to the cost of gas. C is equal to the, I'll put a lowercase b here. C is equal to the distance. And let's say X is equal to the cost of trip. There, I defined some variables. It's one of the things that they made you practice doing again and again and again in the early chapters. I can make an equation out of this. X, the cost of the trip. is going to be equal to, well, what did I do here? I just multiplied these three things. X is equal to ABC. That's what I did here. I take my A, which is the gas consumption, which is 20 over 100. I multiply it by my B, which is the cost of gas, the $1.15 per liter. I multiply that by the C, which is my distance, the 80 kilometers. And I don't need to show this. I already did it up here, right? X will look like this, 0.2. I'll write it out showing the original number. X will look like 20 over 100 times 1.15 times 80. Same thing I did here. But this time, instead of just doing calculations, I expressed it as an algebraic model defining variables. And the calculations are really the same. So basically, anytime you multiply anything, you can express what you're doing as an algebraic model simply by slowing down a bit, defining some variables, and then doing the same calculation you were going to do anyway. Geometry. So we have all of this stuff from chapter 5 that's about geometry. Why is that there? Because so many of the situations that we can make up to give a student, to prove the student understands the math, are geometrical in nature. So none of these are very geometrical. I could turn this pie cut into 24 slices into a geometrical situation if I want. The pie would be a circle. Each of the slices would be sort of triangular in shape. So think about it. When you do geometry, are you using an algebraic model? Well, yes, if you want to. How about the formula? How about the formula for volume of a cone? That's equal to pi r squared h over 3. This only makes sense if we know that h is the height of the cone, r is the radius of the cone, pi is 3.14 if we wish. We can say we're allowed rounding pi to 3.14 in this course, so I'm just going to define pi as 3.14. And we should say also the V is equal to the volume. Okay, so I'm doing all that algebraic model stuff. I'm defining variables, and then I have this equation. That's what the formula is. And then I plug values in and I solve. So anytime you're doing any geometry, and you're able to express it as an algebraic model with variables defined. So the problem isn't, I have this great big situation on my exam, and they want me to give an algebraic model and I don't see one. No, the problem is I see too many algebraic models. This great big situation on my exam, with all the numbers they give me, is giving me all of these opportunities to multiply things and do other mathematical simplifications. And I can choose to express that with the variables and the equation if I want. So I'm going to pick, in a question where they ask for an algebraic model, for instance, I'm going to pick, say, what I think is the most important calculation that I did to answer that question. And I'm going to express that one using the language and structure of an algebraic model, and then I'm satisfying what they asked for. Last things to talk about are the three types of model that the focus of this book is on. And we have all three of them here. We have, I'll get rid of the gas consumption example for now. We'll just look at the top three here. Reminder, the boat taxi is an algebraic model in y equals ax plus b form. Y is equal to 3x plus 10. This only makes sense if I say x is equal to the number of kilometers, y is equal to the total cost. I just made an algebraic model in y equals ax plus b form, and I can plug 30 kilometers into it and solve. Dollars. Okay, don't forget the unit measure. So I did everything algebraic model style about a y equals ax plus b situation. I'm going to do one other example here, which is, wait, what if I spent $60? How many kilometers did I go? I can be asked that. There's two variables in this. There's the number of kilometers and there's the cost. So yeah, it's easy and fast if we plug in the number of kilometers and solve for the cost, but we can do it the other way around. So if 60 is the total cost, It has to be equal to 3x plus 10. And now I'm doing some algebra, and now this is good because it's starting to show some of that moving things left and right across the equal sign math that so much emphasis was put on in early chapters, but which most of my models are not requiring me to do. So 60 minus 10 equals 3x. I'm doing the shortcut. I moved the 10 to the other side. It became negative. 50 equals 3x. I divide both sides by 3. My x is isolated and is equal to 16.7. And that was a total, no, that was a number of kilometers. So my unit of measure is kilometers. I've answered the question. And I did a little bit more with the algebra this time. Okay, let's take a look at the pi. The pi is an example of the inverse. And the rule for the inverse takes the form y equals k over x. Remember that one. If I define x as the number of people, and y as the number of slices per person, then y equals, kx turns into y equals 24 over x. The k, the proportionality constant, is 24. And now I can answer a question. Okay, so what if there are 8 people? Y equals 24 over 8. Which is 3, so therefore there are 3 slices per person. What if I plug in a slices per person? I can do that. What if I want it to be 4 slices per person? 4 is equal to 24 over x. I have this weird situation where the variable is in the denominator. I can do the trade, which is the fast way of showing it. And it means that there must have been 6 people. Does that make sense? Let's verify it. 6 people times 4 slices per person is 24 slices. Yeah, it works. I can do the same situation. I can create a second algebraic model that has to do with the money instead of the number of slices. So y equals k over x. Again, it's inverse because a certain number of people are sharing this many slices, but a certain number of people are also sharing this cost. Well, it depends. You can have one generous person who pays the whole $48 for the pie. But what if we're going to each pay our share for the pie? So if you have x as number of people, again, and y as cost in dollars per person, then y equals kx becomes y equals 48 over x. Notice how the k is 48 now because of the way I defined my variables. So y equals 48 over x. Okay, there are 12 people. Y equals 48 over 12 equals $4 that each person has to pay. It makes sense. I was able to make 2 different inverse algebraic models from this pi situation because the English language presentation of the problem gave me enough information so that I could do 2 different ones. That's interesting. And finally, we have the main one, because the inverse isn't the main focus of this book, but it's in there, and you have to know it, you have to be able to handle it when you get it. And the y equals ax plus b is also not the main focus, but it's in there too. You have to be able to deal with it. But the main focus is the y equals kx. And that was the student using up pencil situation. Y equals 7x. My k is 7 because each student uses 7 pencils. So for students, I plug that in. First I define my variables. X equals number of students. Y equals number of pencils. In total for all the students. I'll write that in total. Because 7 was already a number of pencils, but that's the proportionality constant. So with 4 students, y equals 7 times 4 equals 28 pencils. I've answered a question. I answered the question using an algebraic model for which I defined the variables, for which I figured out what the proportionality constant had to be. being able to do this is the main thrust of the course. If I can do that, it means that any situation that I get in a final exam or a pretest or a scored activity where someone's saying, what's your algebraic model? I know the answer to that question. And if a student is trying to do this course and they're asked by a teacher, okay, here's a situation, what's your algebraic model? And the student has no idea what the teacher's talking about, it means that that student needs more time in this book because it's the main point of the book.